All right, we're going to look here at section 5, which are some applications of the equilibrium constant. And the first one I want to talk about is the extent of a reaction. And we actually already talked about this, so it should be hopefully a little bit of a review. The magnitude of the constant tells you the extent of the reaction. If you have a K that is way bigger than 1, like this example here shows, that means you have lots of products. If you have a K way less than 1, that means you have a lot of reactants. It's all about because it's reactants over products. And so that's just what we're looking at here. I mean, like I said, we already kind of talked about this one. K is greater than 1, it lies to the right because we have mostly products. If K is less than 1, then it lies to the left, and it is mostly reactants. All right, that's going to lead us into then a reaction quotient. Okay, and with reaction quotient, it's also good to know which way a mixture will shift and whether or not it's at equilibrium. And we know that based on what we call a reaction quotient. If I give you a mixture with these concentrations of these certain things, I want to be able to say, okay, well, it's going to shift left, or it's going to shift right, or it's at equilibrium, so it's not going to go anywhere at all. Okay. Well, if your reactants over your product is equal to 0, then it will shift to replace it. So whatever you are adding or whatever you are having, then it's going to shift to replace that. Okay. All non-zero problems, you need to find the reaction quotient, which is a uppercase Q, and we use initial concentrations in the expression. And it looks just like an equilibrium expression, except for it's a Q. Q is equal to the concentration of my products over my reactants, but they are I's. They are my initials. So if these two are 0, then that means that we're going to look at, it'll shift to then replace that, whichever one, okay? But if they're not 0, then we have to look at kind of what our K is, okay? And again, we're using initial concentration. So the example here we have is with ammonia. Okay, and I have N2 plus 3H2 yields 2NH3. And again, it has a double arrow. Notice how it's the same thing as before with the products over reactants. We have the 3 and the 2. Sometimes you'll see O's down here, or you can see I's, either one. I usually put I's, but some books will put O's there. And then there are 3 possible cases for comparing Q and K to then determine which way this particular reaction is going to shift. Okay, so if I have a mixture, which way is it going to go? All right, now if Q is equal to K, then that means it is at equilibrium, and there's going to be no shift. That means, okay, that my K and my Q are equal. So what I have right now is that I actually have equilibrium, because my initial concentrations are what my equilibrium concentrations should be. So it's not going to go anywhere. Now, if you have a mixture where my Q is greater than my K, then that means that I have too many products initially. Okay, so Q is greater than K. I have too many products initially, and so it's going to shift to the left. And that's because, remember, it's products over reactants. So if my Q is bigger, that means I have too much of this stuff on top because my number is too big. So I need to shift to get rid of all these products. So it's going to go to the left. So if Q is greater than K, what we have right here, it's going to go to the left. Now the other way, then, if I have Q is less than K, now I have too many reactants. It's going to shift right to get rid of those reactants. And like I said, it's going to shift to the right. Because again, we have products over reactants, and it's too small. So this number right here is too little. So I need to make more product to make this number bigger, and then we end up with then our equilibrium eventually. Okay, so let's try this example here. I'm going to make ammonia. We give the constant for equilibrium. Okay, and I want to know which way the system will shift to reach equilibrium. Okay, so let's look back at our Q here. Q is products over reactants. And it's the same equation we were looking at before with the N2 plus 3H2 yields 2NH3. So I'm going to have NH3 squared over N2 times H2 cubed. I'm going to do that for all 3 of them. So go ahead and do that for all 3 of them, and then we're going to look at the numbers and see which way they're going to go. Okay, so I end up with these three values here. Okay, the first one has 1.3 times 10 to the 7th, then we have 0.06, and then we have 2 times 10 to the negative 3rd. Now, my Q, okay, is actually, or I'm sorry, my K originally is 0.06, they tell me in the problem. So B is the easiest one here. This one is not going to shift anywhere because it's already at equilibrium. All right, now the question is, which way are these two going to go? Well, here, my Q is way bigger than my K. If Q is bigger than K, that means I have too many products, so it needs to go left to eat those products up or use the products up. And the other way, here, my Q is way less than my K, and negative 30 smaller, which means that I need to move to the right, okay, because my reactant number is too big. Okay, so now we're going to calculate equilibrium pressures and concentrations. And the first problem here is going to be a little bit easier because it says consider an experiment in which gases N2O4 is placed in a flask and allowed to reach equilibrium at a temperature where Kp is equal to 0.133. At equilibrium, the pressure of N2O4 is found to be 2.71 atmospheres. Calculate the equilibrium pressure of NO2. Well, like I said, this one's actually a little bit easier than the next problem we're going to look at. Because if I write my Kp expression, it's going to be P NO2, it's going to be squared over pressure of N2O4. They give me the Kp of 0.133. I don't know my NO2 pressure, but I do know my bottom pressure. So all we do is we cross multiply, take the square root, and I'm going to get a pressure of NO2 to be 0.600 atmospheres. So that's really easy. If you know one of the equilibrium concentrations or pressures, you can know the other one as long as you know the K. But sometimes you're not given any equilibrium concentrations, just the initial ones. And so we have to use a little bit of stoichiometry and a little bit of our initial values in our K to figure out exactly what these equilibrium concentrations are. And this is actually what we're going to be doing for a lot of chapters here. So you need to pay attention here and make sure we can do these. Okay, carbon monoxide reacts with steam. All right, my reaction, CO2 reacts with steam, H2O. These are both gases, so we're good here. Okay, and it produces carbon dioxide and hydrogen. Okay, so we're all gases, so we're good here. I don't need to get rid of anything in my equilibrium expression. It gives me the equilibrium constant, and I have 1 mole of each one and mixed in 1 liter, so that's nice because they're all going to be 1 molar. All right, write the equilibrium expression and calculate the initial concentrations. Well, my expression here is K equals, and everything is all ones, CO2 times H2 equals CO times H2O. And what's nice about this one, like I said, is all of them are the same. All my initial concentrations then are 1 mole per every liter, which is going to be 1 molar. So that's going to make our life really easy here. Okay, now I'm going to calculate Q and decide which way the equilibrium is going to shift. Now you have one of everything. That includes products and reactants. Okay, so Q is the same thing as K, just with initial values. So my initial values are all 1, so I'm going to have 1 times 1 over 1 times 1, okay, which is going to be, oh look at that, my Q is 1. And now I compare that to my K. Now the K value is actually 5.10. So if my K is 5.10, how does that compare to 1? Well, Q is less than K. If Q is less than K, that means that I have too many reactants. My bottom number here, one of them is too big, so it's going to shift to the right to restore my equilibrium back. Now the question becomes, how much does it shift by? And that's where we get a lot of chapter material here, okay? So we're going to draw what we call ice tables. So you start off with the equation up top, kind of spread it out a little bit, and these are all double arrows. And we draw what we call ice tables, and they go ice, C, E. I stands for initial. My initial concentrations for all of these are 1. C stands for change. We're going to figure out how much this is going to shift by. Well, we don't know. They don't tell you. I just know that's going to go right. Well, if it goes right, that means that these numbers here on the product side are going to get bigger, so they're going to be positive. These numbers here on the left are going to get smaller, so it's going to be negative. Well, since my reaction here is all 1 to 1 to 1 to 1, that means whatever I lose on the left side, I'm going to gain on the right side. So we're going to make them all x. If you had a coefficient there, 2 or 3 or 4, then it would be 2 or 3 or 4x, depending on which ones had the coefficient there. So my equilibrium concentration is the E. We kind of add them together. So you get 1 minus x, 1 minus x, 1 plus x, 1 plus x. And we're going to substitute our equilibrium concentrations into the expression and calculate the concentration, because everything is x, so I can just combine all my like terms and then I will get my equilibrium concentration. It's going to be 5.1 because that is my K. It's products over reactants. Well, everything is pretty much the same. My products, though, are the positive ones. All right, the ones on the right here is my products. So I'm going to have 1.0 plus x times 1.0 plus x all over 1.0 minus x times 1.0 minus x. And what's nice about this one is that we can kind of combine these terms here, and I can end up with, you can either FOIL it if you want to. I would tend to go this route, which is going to be just have them as squared. Well, if they're both squared, how do you get rid of a square? You take the square root. That's kind of what I would do personally. Makes life a little easier, but you can FOIL that out if you would like. I'm going to use the shortcut though. And we're going to have 2.258 is equal to 1.0 plus x all over 1.0 minus x. And so we do a little algebra. We're going to solve. We cross multiply. And we should then combine our like terms, and we get x to be 0.386. That's great. That's not what they're asking. They asked us to calculate the equilibrium concentrations of all species. So that means all of my products. So that means for CO2 and for H2, it was 1 plus x. So I take 1 plus my x, which is 1.386. For all of my reactants, then I take 1 minus x. So that would be my CO and the H2O. Those two are going to be 1 minus, which is going to be 0.614. And that is what they're asking for, those two concentrations, because two of them each have the same. All right, go ahead and try the next one. Okay, if we look at this next one, okay, we have our 2.0, that's our 2 molar, okay. I know it's 2 molar as my initial because I have 3 moles in a 1.5 liter flask. Well, 3 moles for every 1.5 liters is going to be 2, okay. I figured out then my Q. I put 2 for all those in the green. Figured out my Q and which way it's going to go. Well, my Q is 1, and my K is way bigger than that. My K is 115. So it's going to shift to the right to make more products because I have too many reactants. So it shifts to the right. So we go negative x plus 2x. This is 2x because this is a 2. Remember I mentioned that in the last problem. And then I just go straight down the column for the E. 2 minus x, 2 minus x, 2 plus 2x. What we do this time is we again combine our like terms. I get 115 equals 2 plus 2x squared over 2 minus x squared. Take the square root to get rid of these squared terms. And then we end up solving, and we get 1.528 as my x. It asks for the equilibrium concentrations. So I take 2 minus 1.528 because H2 and F2 are 2 minus x, and HF is 2 plus 2 times x. So it's 5.056.